everyone. Thank you all for this opportunity. So the project that we've got is a real life example or an application, which is using an AI model to predict how many people are there within a GMP facility. And I'll explain this as we go on, the practical application of this. So, what is an AI solution, right? So in context with what we have developed, we just wanted to define, what defines an AI solution. AI solution is, the model and the application, everything that we develop, but also how it correlates with the real life, right? So is there any quantifiable social benefit? What is the process? At what stage will we use this model, right? How is it, preventing us or preventing violations? How is it supporting humans? So it's a combination of multiple factors which actually help us build a business case in a real life scenario whenever you need investments, funding, or within a company or outside a company, right? At the end of the day, it all comes to solving practical problems, and how you quantify it is by building practical business case around it. And all these factors which I just defined, get together to build the business case. Yeah. So just to give you a quick background, right? So our AI, the application that we built will help us reduce the bioburden within a manufacturing facility in a pharma industry. Now, what does bioburden mean, right? So what happens is when a person enters into a manufacturing facility, there are a lot of things that come out of a person, right? The air that we breathe, we don't notice it, but there are, small skin particles that fall out of a body. So these actually are called bioburden, and they actually contaminate the manufacturing work that happens within a facility. Now, for example, if I'm making a medicine or a drug, this bioburden has a potential to contaminate the drug, and hence the regulatory authorities like FDA or EMA have some guidelines on restricting these bioburdens when products are released from a manufacturing facility. Now, if you just quickly go through the slide, right? So there are, amongst the top 5 reasons why products are recalled by FDA from 2009 to 2017, you would see, bacterial contamination, which is a form of bioburden, is one of them, right? And once a bioburden or, once a facility is contaminated, you have to stop your production. And, and its impact can be both financial and from a timeline perspective, right? So in terms of commercial, right, if you were to look at the best-selling drug in the market, Humira, which sells about $19 billion a year, if you were to stop production for a month, the losses, although it could be done there would be multiple facilities doing this, but if it were restricted to a single facility, the loss could go all the way up to about $1 billion. Now, once there is a manufacturing, once the manufacturing is ongoing, there is some raw material, other things that are already in the process. Now that could have some losses. So, to sum it all, there will be a huge financial loss as well as delay in timeline once you identify there is contamination within a facility. And this bioburden, as a consequence, the bioburden testing market is a huge market. It itself is $1 billion market, and it's growing at about 12-13% year on year. Yeah, Nitin, over to you. Thanks.
Yeah, hi everyone. So our objective of this project was to solve one of the major problems in biopharma manufacturing. So we manufacture monoclonal antibodies. So monoclonal antibodies are normally manufactured in a sterile environment. So where you have to maintain good manufacturing practice, and the area should be clean and without any kind of bioburdens. So if you see the major sources of clean room contamination, it's like people, water, air and ventilation, which goes inside the clean room and goes out, the surfaces of the clean room, and the transport of items which comes in and out of the clean room. So what we are focusing in this project is how to avoid contamination or bioburden excursion through people. So people, basically humans, they shed a high number of skin cells, mostly skin flakes. So this clean, even if we wear clean room garments, which can control to an extent to control the shedding of the skin cells to the room, but there are some portions like eyes or face which is exposed, and then you will get some skin cells which are shedding into the clean room. So basically, we cannot completely avoid this phenomenon, but we can control it by reducing the count by defining like how much amount of like how much count of the people can enter a room at some moment, or like when some operations are going on. So if I go to our existing setup, so this is our existing setup. For example, this is our drug manufacturing block, and there are some rooms where your maximum number of people allowed is only one. You cannot have more than one people. Second means there are some other rooms which are larger rooms, which can accommodate more than one people. It's not like about accommodation, but if it is more than one or two, it can lead to bioburden excursion. So that's why we have these stickers pasted on the rooms, means at the entry of the rooms, to just notify the people who is entering that there should not be more than like 1, 2, 3, or 10 people. And recently we have installed CCTV cameras at the in the clean room facilities. They are at the entry of the room, exit of the room, and in the middle of the room. So to just like check the activities inside the clean room. So so how do we like monitor the CCTV footage right now is like we are having a CCTV monitoring desk, and a person is dedicated to monitor that CCTV, like a security kind of a thing, who are like dedicatedly monitoring the CCTV footage and monitoring the violations and then reporting it to the facility head. Now facility head is actually helpless even if there is a violation which is reported. So how do you control it? Means even if you tell to a cross-functional team member that your persons are like violating, and then you notify them, every time it is not possible to control that because there is no automatic measures to control it. So his headache will even increase when there are some violations and how to control it. So so this was the like essence of, or like this was the point when where we started thinking of this project. So our proposed AI based solution is like we'll have a backend AI engine which will be detecting the persons and then counting the persons and reporting the violations, and then those violations and even the person counting system will also display a dynamic count of the people who is inside that particular room. So for example, in this room, like what is the count, it will be displayed here, so that person who is entering the room is already aware that there are like already 10 people inside the room and he should not enter, or he should wait for somebody to go out. So that dynamic headcount display is something which we are planning to implement here at the entry, so that the operator will be conscious before entering the clean room. So if the operator is conscious and then entering the clean room, then it's a conscious violation. So that is a different case. But now the problem is that you are having a like a sticker, and then the operator is not aware how many people are like inside the facility, and he can just blindly go inside. So that is what we are planning to control, and we don't need a monitoring desk hereafter. So we are planning to remove this monitoring desk. What we are getting from an AI application is a daily room occupancy report, like in a day-to-day basis, how many excursions happened in a day, that will be reported at the end of the day to facility head as a report. And facility head also like don't have to review the video footage. He has to just see the report and then say that it's all okay, or there are some troubles which he has to worry. So those are the actions we were planning to do, and if required, if facility head feels that there is some kind of digression required in the problem, then he can check the filtered violation videos. So we have like filtered some whenever there is a violation, we have like recorded those video clips and kept in a folder for the facility head to review. So, and even we are having the violated image also, we'll be showing it in ahead. So what are our like analytical reports which comes out of this backend model is this. Actually, this is the main report which comes out of it, which is the clean room occupancy report for that particular room. So this room name is M2BR8. So this is our bioreactor room, and just this is just for like showing the excursions that we have limited the number of people to 3, but we can like have more than 3 people. So whenever there is like more than 2 people, when it reaches 3 and more, like 4 or something, you will have that excursion, and this report will have a red kind of lining here. So if you see here in this particular video clip or in a particular day, you will have like this many excursions and this many like green areas where there is no excursion, like it was within the limit. So this is the report, primary report, which facility head can review and then go ahead. If you want to digress into the issue, then we are storing violation video clips, which are like 10 seconds before the violation and 10 seconds after the violation. So that are also recorded and saved in a folder. And also we are having violation images also, which we have like boxed it with the persons, the number of persons, and then we have shown on the top that what is the number of persons we have detected. Like for example, here you can see that violation alert and persons detected is 4. So this is one of the other output which we are like storing in the folder of room. So these are all like room based folders. So each room will have each folder, and each folder will have like violated videos and violated images and this report of trend of that day. So I'll just show you one other report which looks fairly good. So it's like total green and blue, like there is nothing, there is no violation, and there is no occupancy during this period. There's one more report which has some sort of violations. For example, at 44 seconds, there's a violation and you're having a video clip and image for it, and you are having the number of persons violated and boxed around it. And we have actually inverted the colors here to show that it's a violation. So actually it's a blue color floor and we have made it yellow, and it's a blue color person, but we have made it yellow to just show that it's a violation. So how we did this backend model is like, we didn't had a data set, so we have made our own data set. We have like taken the video footage of CCTV and then split it into images, and then those images we have created bounding box using LabelMG app. And then LabelMG app usually gives this notepad file along with the image. When you make a bounding box, you will get a notepad file with the box parameters and what is the number of persons we are detecting here. So this is the way we have done the training for like lot of images, around like 100 to 120 images we have done like this for training the YOLO model. So from the code flow perspective, Rahul, I will hand over it to you to explain the code flow.
Yeah, thanks, Nitin. So yeah, this is a end-to-end pipeline of our project code flow. So here, like as Nitin talked about, we captured the video from this CCTV camera, and then using OpenCV on this Python package, we have split those video into many videos and then into frames, and then in those in those images we have make that bounding boxes, and those were then acting as the input to this YOLO before model. And once we have done this modeling and get this object count, and then we have a Python script for object counting. And again, with the use of OpenCV, we have make this bounding box and count information embedded in those images, and generate the mini video of the vaulted frames. And using this matplotlib, we have generated the report, so that Nitin has talked about. So yeah, in this way we have used OpenCV and YOLO before model to complete the end-to-end task in the backend. So yeah, and that's all for this code flow. And now Sarvagi will talk about the model itself.
Thanks, Rahul. The primary model that we used was the YOLO V4. And it's a one-stage detection model, which means that the object localization, that is detecting the object, and the classification, it happens in one stage. And there are several two-stage detection model, but YOLO is a one-stage detection model. So if we could go to the next slide, we'll see that YOLO architecture has basically three parts: the backbone, the neck, and the head. The backbone, it's basically a dense net. A dense net is basically, it consists of convolutional and batch normalization and pooling layers. And what is done is that from the previous layer, the input is taken, and the current output from the current layer, the output is taken, and they both are concatenated together and fed to the next block of the dense net. So what this does is it sort of removes any layer that might be redundant, because this is a very deep architecture. So what can happen is that some of the blocks, the information might not get propagated fully forward. So what happens? So this way, all the information of the previous layers is carried forward to all the layers forward. And A variation of DenseNet, which is cross-stage partial DenseNet, is used in YOLO, in which the output is split in the output of the previous layer is split into two parts. So one of them, as you can see here, it goes to the partial dense block, and the next one, it just bypasses everything and sort of goes to the last transition layer. So what this does is removes the it removes some of the computational burden from the architecture. Now coming to the neck is basically all the feature maps that have been produced by the backbone. It basically sums it all up for the head to detect it. So for this, we used two special technologies, I would say, that are incorporated. One is the spatial pooling layers. The spatial pooling layers, what they do is that the feature maps that come from the DenseNet, they are split into multiple spatial bits of some size. For example, in the neck portion in the above, you can see that there is one into 256 dimension, another is 4, and another is 16. So all these fixed spatial bits are created, and then they are all max pooled and concatenated together to create a fixed dimension output. So one advantage of this, of using the spatial pyramid pooling layer, is that we can like the fixed connection layers, which are onward, that are in the forward architecture or the upper layers, they always require a fixed tensor. But the convolutional layers can take image of any size. So what the spatial pyramid pooling layer does is it can take images of any size and it can convert that into the fixed length representation, which will be apt for that particular fixed fully connected layer. The second technology that is used is the PAN net. The PAN net, what it does is, so there are bottom up propagation and up down propagation happening for the different features. And what does it takes a lot of time in a deep architecture. So it basically bypasses everything. You can see a red arrow here. So from P1, it directly goes to P5, the information, and then it can also go to the next one, the green one, to the N5, which is basically sort of the semantic information is not lost this way, like going through different layers. So this is incorporated. Next, we go to the head. The head has many uh, technologies that are incorporated, but the main ones are the IOU, the intersection over union, which basically predicts the bounding box for that given object classification. So the modification that YOLO uses is the center IOU, which basically also takes into account the center coordinate and the aspect ratio to predict a more accurate bounding box. The next is the sensitivity elimination tool, which basically what it does is the bounding box, like we see here, TX, TY, these are all the predictions of the bounding box that is given by the model. So what this does is looking at the upper corner of the image, that is CX, CY, it basically tries to conform the bounding box in such a way so as to reduce the sensitivity. So this is the entire YOLO architecture. So we then fine-tuned it with the data set that we created. And now I think Nitin will show the video of the demo.
Yeah, I'll just show you one live streaming which we are doing now. So here, we'll have like folders where we are having the room footages coming in. And for example, I have started for the PLC room, and here in the detections folder, we'll have like multiple folders like occupancy trend, violated video, and violations. So in violations, if you see now, so you will have these images, violated images, with stamping of like how many people were present and what is the timestamp, like 151 second it is showing here. And in the actual video streaming, it will be timestamped with the date and time. And if you see, it will like show you the actual boundary boxes and the persons detected. And similarly, we'll have in the detections violated video, where we will having violated videos of that particular rooms 10 seconds before and 10 seconds after the violations, which are getting populated. If you see, like now only it is detected and it has started like storing it here. It's 643, 640. It's going on now. And here in the another feature is occupancy trend. So in occupancy trend, you will have the images of each room occupancy. So for example, this is the PLC room occupancy, which we have recently done. Yeah, this is all about it. Thank you.